Minds. I'm Yvonne Stapp, and I welcome you to Contemporary Science Issues and Innovations for Science for the Public. Today, we talk with an astronomer working on one of the most exciting projects of this century, the project that will measure the accelerating expansion of the universe to a new degree of accuracy. Our guest is Paul Martini, professor of astronomy at The Ohio State University and a research fellow this year at the Radcliffe Institute for Advanced Research. Dr. Martini is both an observational astronomer specializing in quasars and a few other things, and an instrumentalist, one who is involved in the design of the technology and the equipment for this kind of project. And the project is the Dark Energy Spectrographic Instrument. It is quite unique, and Dr. Martini will give us some background about the issue of the accelerating expansion of the universe, the huge challenge of measuring that very accurately, and then the project itself, the equipment itself, which is quite exciting, and then the implications of this survey, a 5-year survey, the implications for physics and possibly and for astronomy. And Dr. Martini, welcome and thank you very much for joining us.
Thank you very much. It's a great pleasure to be here.
And I would like to start with just some background. There are a bunch of terms here, quasars and accelerating expansion and a whole lot of things. To get an idea of how these fit together, what is this issue of acceleration?
Great. The accelerating expansion of the universe is really one of the most remarkable discoveries of the last few decades. And it's remarkable in the sense that it was more or less completely unexpected. It is very counterintuitive. So the basic observation is that our universe is expanding. We know that the universe formed billions and billions of years ago in a Big Bang explosion that produced all of space and time. And the universe has been expanding outward ever since then, or is increasing in size ever since then. The expectation that we had, based upon our understanding of gravity, is that the mass in the universe would work to slow down that expansion, decrease the trajectories of objects relative to one another over time. Instead, what was discovered in the late 90s was that the universe's expansion started to accelerate about 4 billion years ago. And this was very counterintuitive. It's somewhat like if you took a ball and threw it up in the air, and instead of it slowing down because of the force of gravity, after a certain point in time, it started to speed up again and accelerate even faster away from you.
Now, so here are all these surprises, and I think one of the major concerns is how you measure that. You're an expert on quasars, and quasars are very central to this project. Is that correct? To this measuring?
Yes, the DESI project has
Yes.
a number of different types of astrophysical sources that it studies in order to measure the accelerating expansion of the universe. One of those is quasars. The others that it uses are various types of galaxies. Quasars are the most luminous objects in the universe, and they are really critical for studying the expansion rate at the largest distances. And so all of our most distant objects are quasars. Quasars are objects that are more luminous than galaxies. They are produced by the accretion of matter onto supermassive black holes. And this accretion process can produce more light in a region of the galaxy that's about the size of our solar system, in such a small region, it produces more light than an entire galaxy. Quasars can outshine the host galaxy in which they live by a factor of 100 or even more.
Can I get one little clarification about quasars? I think we non-astronomers tend to think of those as big stars or something. That's something, but you're the expert on this, and they are related to black holes. Is it in galaxies, massive, supermassive black holes, or is that not true?
Yes, that's absolutely right. So a quasar is a galaxy whose central supermassive black hole is rapidly accreting enormous amounts of gas and dust from its host galaxy, from its immediate environment. So we know from careful studies over the last few decades that all massive galaxies in the universe have a supermassive black hole at the center. And by supermassive, I mean a black hole that is millions to even billions of times more massive than our sun.
I see.
And so a quasar is the phenomenon that results if that black hole is actively accreting matter from its surrounding environments. If matter is falling onto the black hole, that can produce a lot of heat, a lot of energy release, and that gives a quasar its incredible luminosity.
Okay, I just needed to get that clarification because this is so central, apparently, to this measure that you're going to be making, I think. But one more thing before we get into this project itself is there is the difficulty of measuring this acceleration. Apparently, it's a huge challenge, and for years we've had something called the Hubble constant, and now we have something called the Hubble tension.
Mm-hmm.
And I think your project is directly involved with settling some issues that way about the expansion and what to call that.
Well, we will certainly be measuring the expansion rate for the universe much better than previous studies. The current state-of-the-art project, which recently released their results over the summer, was a project called EBOS, for the Extended Baryon Oscillation Spectroscopic Survey. And that project measured the expansion history of the universe using close to 4 million objects. And what DESI hopes to accomplish is to extend that by about a factor of 10, about an order of magnitude increase in sample size. And that much larger sample will give us much higher precision in our measurement of the cosmic expansion history.
Okay.
So with regard to the Hubble constant, the Hubble constant is a measurement. It is a quantity that describes the relationship between the distance of two objects in the nearby universe and how fast they appear to be receding from us, a quantity astronomers call the redshift. That relationship between distance and recession velocity is described by the Hubble constant because the relationship is linear, meaning that it could be fit by a straight line.
Okay, now then we should talk about this project, which just sounds quite unique in the way that it measures the number of galaxies it's measuring, and then the way it will present that data, I guess, in the end. But can you tell us, please, about DESI, and you can spell it out for us now?
I'd love to. I'm super excited about working on DESI. It is by far the most sophisticated and fascinating project I've been involved with. It's a huge collaboration of scientists, both within the US and internationally. It is led by the Department of Energy's Office of Science and the Lawrence Berkeley Laboratory, but also has university partners and international groups that are involved. And the size of the project is important because the amount of instrumentation we've had to produce in order to increase a sample size by an order of magnitude, by a factor of 10, required a lot of technological development and just a lot of hard work by a lot of scientists and engineers. So to give you a sense of the scope of the project, we are using the Mayall 4-meter telescope that is located out at the Kitt Peak National Observatory near Tucson, Arizona. And we have built a new wide field corrector system, which is a new optical element that will allow us to image a large region of the sky at once. And then we feed the light from that optical corrector into 5,000 robotically positioned fiber optics cables that then end up in our new set of 10 state-of-the-art spectrographs. And with this, we're able to collect the light from 5,000 objects at a time, and that allows us to much more efficiently map the sky with our spectroscopic survey than previous projects.
Okay, now, so this is huge. I think in terms of the number of objects it will survey, and this is over 5 years, is that correct? That data is over 5 years.
That's right.
Is this the largest amount of data, the largest number of galaxies that they will check?
Our plan is to obtain spectra and measure redshifts or recession velocities for 35 million galaxies and quasars over the course of just 5 years. And to put that in context, the largest survey to date, the one I mentioned earlier that just finished, it mapped close to 4 million objects, or about 4 million objects. So we're mapping about 10 times as many in actually a shorter period of time than that project. But that's only possible with this substantial technological development.
Then the next thing is how does it collect that data? What does it what do things like the baryon acoustic oscillation and these kinds of terms, what do they mean? How does it gather that data?
And DESI collects its data by positioning lots of fiber optics cables, 5,000 fiber optics cables, at the locations of individual sources that it has pre-selected from very detailed imaging of the night sky. And we position a fiber optic cable that will transmit light, just like fiber optics are used in telecommunications. And that light goes from the focal plane, which is up high above the primary mirror of the telescope, and goes through a fiber cable that's about 50 meters in length and is fed into a spectrograph that then disperses the light into its constituent colors. And we use the locations of various well-established features within the spectra of galaxies, such as the locations of hydrogen emission or absorption features, to determine how fast the object is moving away from us. And so that's how we measure the redshift of the source. And I could actually show a picture of the telescope now.
Please do, yes.
So this is an image of the Mayall telescope back when we were installing the DESI instrumentation. And this is showing the telescope inside of its dome. The telescope of the telescope's primary mirror is 4 meters in diameter, and that is located about here, if you can see my cursor.
Yes.
And then the focal point of the telescope, what we call the prime focus, because it's above the primary mirror, is located up here. And this picture was taken during the installation of the new corrector optics for DESI. And those are really remarkable optics in and of themselves. They are made up, the primary or the corrector system for DESI is made up of 6 lenses, each of which are about 1 meter in diameter, and they are polished to a fraction of the wavelength of light. And that was a huge development project on its own. And then the focal surface, the focal plane of DESI, which has the fiber optics in their positioners, is located above the corrector and would be installed up here in this picture. And that has since occurred.
Okay, So it's going to collect this huge amount of data. It's a rather unique instrument. And then how do you select which objects? You've got these thousands of objects, and there are billions of objects out there. You must select somehow. How do you do that, and why?
We, in advance of the DESI project, a group led by the Lawrence Berkeley Lab conducted a huge new sky survey called the Legacy Surveys. And they collected data using telescopes at Kitt Peak, the Bok telescope, which is also on Kitt Peak, and then what's called the Dark Energy Camera at the Cerro Tololo Inter-American Observatory. They conducted a large sky survey of what we call the footprint, the area of the sky that DESI will observe with its spectrographs. And that was a multi-year effort by a large team of people as well. And then we select the objects that we want to observe based upon the brightness and the relative brightness of those objects at different wavelengths. And so this combined data at visible wavelengths, as well as in the mid-infrared using data from a NASA satellite called WISE.
I see. And so you have all these objects and the way that to collect that. And then another really interesting, at least from the outside aspect of this, is that this will be cast in 3D. Is that something new? And what would be the advantage?
We use the imaging data to estimate how far away we think sources are, because in order to measure the expansion history of the universe over time, we want to have a large number of sources at a wide range of distances from us. So we can use the imaging data alone to estimate about how far away we think individual sources are, and then that estimate is used to target them for spectroscopic observations. And with spectroscopy, we can then measure their redshifts extremely precisely. And those are the data that we use to measure the baryon acoustic oscillation signal that you mentioned earlier. That is our tool for estimating very robust distances to objects across the expansion history of the universe.
On that issue, why is it so difficult? Well, it seems inherently it must be. These huge distances, we are talking over billions of years. What are some of the problems of measuring that light at these, different times over this vast universe in order to understand this expansion? What are the complications for that? As we're seeing, light is going out in a straight line, but there's a little more to that, I think, that astronomers understand and we don't necessarily.
Yeah, so the big challenge is to very precisely measure this signal called the baryon acoustic oscillation signal. And that is a very subtle effect, and we need a very large sample of galaxies to detect it. So maybe I should first explain what the baryon acoustic oscillation signal is. This is a result of processes in the very early universe, much earlier than what DESI will observe, actually extending in the first just 380,000 years of the existence of our universe. At that time, the universe was very hot, very dense, and in fact, it was so dense that electrons and protons were not connected with one another, and furthermore, that there was pressure of the photons on the electrons and also the positrons or protons that were floating around in space, and that pressure led to something that's kind of like a sound wave, or what we call an acoustic wave, and the fluid in the universe, you can think of that as just a really hot, dense soup. It was sloshing around, and it was sloshing around in particular in the vicinity of significant mass concentrations. The BAO signal that we're looking for, this baryon acoustic oscillation signal, is the signal from the propagation of sound waves out of lots of individual sources of mass concentration, the future galaxies and clusters of galaxies we see today. That signal, like a ripple traveling across a pond, was able to travel out a certain distance until the universe became cool enough and low enough density that electrons and protons could combine with one another, and the pressure went away that was driving those waves. At that point, the electrons and protons were no longer getting pushed around by the photons, and this produced an excess of what we call baryons. This is basically normal matter at a very specific distance from the centers of mass concentrations in the universe. And this is important because this excess of normal matter is always at a very specific scale relative to mass concentrations. It's a very small effect. It's a few percent excess relative to other spatial scales. And it's something that we can only measure with extremely large samples of galaxies, where we look at the relative numbers at a wide range of separations and use that to measure what we call a standard ruler that we can then use to determine the distance.
Now, once they get baryonic matter, our regular typical matter, right, is formed, and then you have this continuing expansion. But I think that you pointed out the expansion occurred at different, there were different rates of acceleration at a couple of different times. So there are two things there why that difference, you know that, and then it's very difficult to measure this with accuracy, this signal with the expansion over time. So the first thing is, how did this slow down and start up? I think you alluded to it, but if we could get it just clear.
Yes, so there are two things I could explain here. One is how the expansion rate of the universe has changed over time, and then how we can measure this.
Yeah.
The expansion rate of the universe was initially slowing down. So after the Big Bang and an early period of what's called inflation, then over billions of years, the expansion rate of the universe and the rate at which galaxies moved apart from one another would gradually decreased. And then about 4 billion years ago, so this is when the universe had been around for about almost 10 billion years at that point, the expansion rate started to increase again. The way we measure that is by looking at galaxies at a wide range of different distances, because the speed of light is finite. And so when we look at objects that are farther away, we're looking at the universe at an earlier time. And what we can measure easily with our experiment with spectroscopy is the redshift or recession velocity of the galaxy. And since that recession velocity is due to the expansion of space itself, that tells us how much of a change there has been in the expansion rate of the universe since the light left that object. Then what we want to measure, the really challenging thing to measure here, is how far away those galaxies actually are. Mm-hmm. And that's why we need the BAO technique, why we need this standard ruler. Because if we go back to the analogy I mentioned earlier with the ball thrown up in the air, if we throw a ball up in the air and then it slows down over time, like we would expect from gravity, then the relationship between how fast it's moving and how far away it is relatively easy to predict. However, if instead it starts accelerating, then the speed at which it's moving away from us is not going to follow the same relationship between distance and speed as it would if it was just slowing down under the influence of gravity. So what we want to do is we want to measure both how far away objects are and how fast they are moving. And we put those together into a cosmological model to study the acceleration rate and then hopefully gain insights into what is causing the cosmic acceleration. The technique that we use for distances, this baryon acoustic oscillation technique, is a standard ruler. And this actually is a fairly simple concept. It's just the implementation is challenging. The simple concept is we all know that if someone was holding up a yardstick, for example, we know how large a yardstick is. And if someone was holding up that yardstick and starts to move away from us, the yardstick is going to appear smaller and smaller the farther they go away. And then with a little bit of trigonometry, remembering angles and relationships between angles and lengths, we could figure out how far away that person is from the apparent angular size of that yardstick. The BAO signal is basically a perfect yardstick for doing cosmology. It's different from a yardstick because it's nearly 500 million light years across and not about a meter. But anyway, if we can measure that at a wide range of different distances, then we can use essentially trigonometry to figure out how far away galaxies are at the redshift that we measure the baryon acoustic oscillation signal.
Okay, so now we understand that you have a very accurate way of measuring, and then with the DESI, you'll have the kind of equipment that can really gather massive data, and you have the techniques available for analyzing that data. Will this tell you anything about dark energy? What I assume you think that dark energy is doing this.
Yes, absolutely. So our goal is to acquire a huge number of measurements of redshifts so that we can measure the baryon acoustic oscillation signal and then the distances to galaxies at a wide range of different redshifts. And with that, we can map out how fast the universe was expanding over a very large fraction of all of cosmic history. And then we can use those data to determine whether or not the accelerating expansion that we observe today is due to what's called a cosmological constant, which could be explained by some negative pressure in the vacuum of space itself, which is commonly referred to as dark energy, or if the accelerating expansion is due to an effect that is changing over the history of the universe, and that might indicate some other explanation beyond the dark energy, beyond just a constant related to the vacuum of space itself. And other explanations that have been proposed are that there is a modification to our understanding of gravity, that it becomes important at very, very large spatial scales beyond the sizes of galaxy clusters. Because if, for example, the force of gravity changed from being attractive, like it is on Earth, and throughout our galaxy and local universe, if it instead became repulsive for objects that were separated by tens to hundreds of millions of light years, then that could potentially explain the accelerating expansion of the universe. Or there could be some new force of nature that we haven't discovered yet, like gravity, electricity and magnetism, the strong and weak nuclear forces. If there's some additional force of nature, that would also be super exciting. And that could also explain the accelerating expansion that we observe.
Oh, that is very exciting. And is that why this project is thought to be, that there is some idea that this will possibly lead to a new physics and some real breakthrough for physics and astronomy in that way, a new direction.
Yes, absolutely. Our hope is to measure the expansion history sufficiently well that we would be able to detect if the accelerating expansion is due to dark energy associated with the vacuum of space itself, or if one of these other explanations is important, namely a modification to general relativity, Einstein's theory of gravity,
Mhm.
or if there is some new force of nature that is at work. And that would be really exciting new physics.
I think it would be. You are living in a fabulous era for astronomers and astrophysics just in general. How long is it going to take to analyze this data? If the survey is 5 years, how long do you expect before you get some of these big answers? That's one thing.
As you mentioned, we plan to be collecting data for 5 years. Within the first year of our regular survey operations, we expect to have a larger sample than has been obtained so far by any previous work. And so it could be as early as then that we will have some exciting new results. I think we will certainly find exciting things no matter what, because we know from experience that whenever we collect new quantities of data and analyze them in new and fundamentally different ways, we always find something exciting. And then by the end of the 5-year survey, we will have a really substantial improvement in our measurement of cosmic acceleration. And that will hopefully be a significant enough improvement that we will be able to see if the universe is still explained by a purely cosmological constant, or if there's something else really interesting happening. I should also add that these data will also let us address a lot of other really exciting topics in fundamental physics. For example, we expect to obtain the best measurement of the sum of neutrino masses from DESI, which is really quite exciting. Neutrino oscillation experiments, observations from solar neutrinos show that neutrinos have mass, but what we don't know is what the sum of the 3 different types of neutrinos add up to. And DESI should be able to determine what that is using observations of large-scale structure. And we also hope to measure what's called the power spectrum of matter fluctuations, which is the distribution of the numbers of mass concentrations or galaxies as a function of spatial scale. And that will tell us something about this mysterious primordial inflation that occurred right after the Big Bang. So we hope to better measure properties of the distribution of matter itself that will give us new insights into the early period of inflation.
Oh, I can't resist asking, since this is very exciting, and it was a shorter period of time than I thought that it would take for you to get real information that's going to resolve a lot of questions. But I can't resist asking a question about that inflation that I think it's always out there. Well, you had the Big Bang, then you had the inflation, and then the rest of the story. And but it seems to me that there have been questions in astrophysics about that inflation. There are some problems. Is it widely accepted the inflation happened as is typically described? Are there any big problems with that affect what you're looking at?
There is very good evidence. I think it is widely accepted that this early inflationary period existed. It is a very good explanation for why the universe is so homogeneous and isotropic on large scales. It's really the only explanation of that. And so we are confident that this inflation period existed, but we don't have a good explanation for what caused the inflation. There are good theories of this that provide very, very plausible explanations of the inflationary epoch. However, it is a very difficult region to probe directly because we don't have good direct measurements of that time. And we hope to study that period by looking at the late time effects of it in our DESI data.
Because that's interesting all by itself. I thought it was very hard to get for reasons you were describing that early period, that first 380 million years or whatever before the atom really formed. And so you had this mess in there to try to figure out but now you think you can analyze that inflationary period.
Well, we think that we can use the distribution of matter in the universe in the data we'll collect from DESI to obtain new insights into what was happening during the inflationary epoch.
I see.
Yeah. So we won't be able to probe back that far in advance, because while in the early universe, it was great that photons and atoms were so dense enough that they produced this baryon acoustic oscillation signal that is great for our cosmology experiments. Unfortunately, that also means that it was basically impossible to see earlier in the universe's history than that, because when the universe was that dense, photons could not travel far at all before they immediately smashed into an atom. And so therefore we have no light from that early time that we can detect. The earliest is this period where the cosmic microwave background formed.
I see. Wow, it's really exciting. Before I let you go, I'd just like to know a little more about the instrumentation itself. The big question is that I guess this is really a leap in terms of the technology and measurement. Is that correct? Is that the case? That can you tell us a little bit about that? Why is this such a huge leap in technology, but could only happen now, I guess?
Yes, and it's because of a number of technological improvements that have occurred over the last several decades. One of the technological improvements has been with fiber positioner technology. So what I mean by that is, in order to collect the light from an object, we are sticking the end of a fiber optics cable on its location on the sky. And then because we have 5,000 fiber optics cables, we have 5,000 of them spread over our focal surface, which is about 1 meter in diameter. In order to efficiently collect the light from those sources, whenever we point to a new area on the sky, the pattern, the kind of constellation-like pattern of objects that we want to observe is different. So when we move the telescope to a new place to collect data, we need to change the locations of all of our fiber optics cables so that they are configured for the pattern of objects that we are currently pointing in. In previous experiments, we have used mechanical plates or mechanical plates to identify in advance and cut actual holes or slits in a piece of metal to mark the locations of the objects relative to one another. And the process of changing between plates is quite time consuming. It can be as long as it takes to actually collect the data. With DESI, we're able to do this changeover in a small fraction, about 10% or less of the time it takes us to collect the data. So we're just able to acquire data and new observations at a much faster rate. And furthermore, we have a much larger number of fiber positioners and fiber optics cables than previous experiments as well. So we have about a factor of 5 times more fiber optics cables than previous experiments, and we can position those for new fields much faster than previous experiments. And this is only possible because we're able to cram lots of little robots into our meter diameter focal surface. We have 5,000 fiber robots, each of which are about the size of a pencil, spread out over a meter diameter circle. And it's challenging to make the robots that small. We actually use these things called brushless DC motors. Each fiber positioner has 2 of these motors. They're only about 4 millimeters in size, quite tiny. And they are able to position the fiber optics cable extremely precisely over what we call its patrol radius, over a region about 10 or so millimeters, 12 millimeters in diameter. So that's one of the big technology breakthroughs, is being able to do this. And this was only possible due to a lot of research and development work at the National Lab. Another big improvement has been in our detector technology. We now have CCD detectors that are able to detect light as red as about 1 micron. So that is quite a bit redder than what can be seen with the human eye. The human eye is sensitive to a wavelength range from about 400 to 700 nanometers. And we're now able to use CCD detectors that can detect light very efficiently out to a micron, which is about 1,000 nanometers. And that's been due to a lot of improvements in semiconductor technology that has enabled improvements in how well we can detect light. And being able to detect redder light translates directly into being able to more efficiently observe galaxies at larger redshifts. And so that has been a significant improvement as well.
Right. I thought, but in just reading a little bit about this, that the robots themselves, that was a huge thing. It seemed like here on the outside, but you've added to that. There are a number of features that are unique to this project, I guess, but also built on the development over time of these technologies that just open up the universe in a very unique way. You've come a long way from ordinary telescopes, right?
When I started as a graduate student, when I would go out to a telescope, I would use a spectrograph that could observe one object at a time. And I would point at an object, collect data for maybe 1 or a few hours, move to another object. And in the course of the night, I might be so fortunate as to observe maybe 8 or 10 objects. Now with the DESI project, I can go to the telescope and we can collect perhaps 100,000 spectra in a single night. And so it's just remarkable how much of a difference that is. And that's thanks to a lot of research and development work. That's critical. And it's that sort of improvement that opens up massive new discovery space.
Right. It's fabulous. What a time to be living. When you were just mentioning this, I was thinking of those old photographs of Hubble, standing on the telescope steps, and he'd be frozen all night.
Yes.
Try to do these measures, which were very complicated, and you couldn't leave the telescope. And now people can download just massive amounts of data, very accurate data, onto computers and do the analysis, I guess, computationally, without having to, being able to do this at a scale that was not possible in the past.
Yes.
How soon are we going to have a big report on this? The articles about this
on the discovery,
on your project, on the first take of the DESI.
We expect to start taking data by the end of the year. We're currently paused because of difficulties getting access to the site, at least with a large enough team of scientists to operate safely due to the COVID-19. But by the end of this year, we're hoping to resume our observations. And within a year, we expect to have a really phenomenal data set. So I expect that about that timescale, we'll have our first results on the accelerating expansion of the universe and some of the other topics I've mentioned as well.
And
So I'm super excited about that.
Yeah, answer some of these big questions that there'll be surely revisions made here. And as you suggested, new physics, maybe whole new directions. You brought up many interesting things. I'm going to get back to you on this issue of scale and gravity. I can't resist that. That's a whole thing by itself, But Dr. Martini, thank you so very much for all this information. I wish you the best success. And I can just hear those champagne bottle corks now, because this is going to be a lot of celebrating, isn't it? It's a whole great leap forward. Thank you very much.
Well, thank you very much for speaking with me. It's been a great pleasure.
And I hope you come to Cambridge soon for Radcliffe. Thank you.
Thank you.